Good morning, Honors Pre-Calculus students. This is Mr. Hazelhorst here with your Chapter 9, Section 6 video. We're going to use this video just to review a concept that you covered last year in Algebra 2, known as the counting rules. So counting rules are used to find the number of possible outcomes for a sequence of events. And this will be important as we begin this chapter on probability. Being able to figure out a number of possible outcomes is important as we deal with different probability settings. As we talk about our counting principles, we have three different rules that we can utilize. We have what's known as the fundamental counting rule, a permutation rule, which can take on three different looks, and the combination rule. And so we're going to deal with each one of these. Again, hopefully this will be a review from your Honors Algebra 2 days. And I would also recommend, as you watch the video, if you have your graphing calculator handy, you might want to pull that out, as we're going to show you how to use the permutation and combination functions on your graphing calculator to work through some of these problems. All right, well, let's jump right into it with a fundamental counting rule problem. We're just going to do an example and use that to give our definition as well. All right. So our example problem here says telephone numbers in the U.S. currently have 10 digits. The first three numbers are the area code and the next 7 are the local telephone number. How many different numbers are possible within each area code? That's our question. All right. So it says, note that at this time a local telephone number cannot begin with 0 or 1. All right. So with that said here, let's just jump right into it. Now, I'm going to just kind of think through this problem out loud, and then we'll compare that to the actual definition of the fundamental counting rule. All right? So in this problem, we just want to know how many numbers are possible within each area code. So we're not looking at all 10 digits. We're really only looking at a 7-digit telephone number. And so when we think about a 7-digit telephone number, what I like to do in these counting rule problems is I like to just kind of draw out with spaces what we're trying to find here. So I've got 7 digits. All right, and now I'm just going to go back, and in each space, I'm going to fill in how many possible options we have in that location. Okay, so in the 7-digit telephone number, we know that a telephone number cannot begin with a 0 or a 1, so we don't have all 10 digits from 0 to 9 available to us. We only have 8 of those digits available to us, right? Because we've got to eliminate the 0 and the 1, okay? In our next spot, well, we don't have any restrictions the rest of the way through. So for all of the rest of the spots, our outcomes are 10. Or our options to form that, I should say, are 10. All right, so according to our fundamental counting rule, says in a series of events, the number of possible outcomes can be found by multiplying the possible outcomes of each individual event. So what we've done here is we've listed out all of the possibilities of each individual event, and the fundamental counting rule says, okay, go back, and now let's just multiply all of these together. So as we do that, we end up with 8 million different outcomes. Okay, and so that's our problem here with the fundamental counting rule. Okay, now one big question to think about in future problems would also be, as I'm doing this problem, is this happening with or without replacement? You know, in our problem, it's okay that we repeat numbers, but in certain situations, sometimes once you make a selection, that item no longer remains, and that then impacts how many possible outcomes there are for future events within the sequence. Okay, so that's something to keep in mind as you deal with your fundamental counting rule. And that's a pretty easy rule to use in those counting rule situations. All right, so let's move on to our next one then. Okay, permutations. Now, if you remember from the opening slide, we have 3 different permutations that can take place within a given set of problems. All right, so the first set of permutations is when we're taking the number of permutations of n elements, all right? N's just representing a certain number, okay? So here's an example. It says, how many permutations are possible for the letters A, B, C, D, E, and F, all right? So we want to know how many different ways can we put these items in order is essentially what's going on here, okay? So this this permutation rule is really an extension of the fundamental counting rule. Right? If I want to put all 6 of these letters in place, right, I have 6 slots that I need to fill, right? 1 letter is going to go in each place. Now notice in this problem, once I select a letter, I wouldn't be able to select it again, okay? So when I go to select my letter for the first individual event within the sequence, I have 6 different letters that I can choose from, all right? Now, it doesn't really matter what letter I choose, but once I've chosen one, I'm now down to 5. And then I'm down to 4, and then 3, and then 2, and then 1, right? And you can see we're multiplying this kind of descending sequence of numbers. Now, another way that this can be written, and this is really the permutation rule, is this could be written as 6, and then we use an exclamation point. It's known as a factorial. All right, 6 factorial. And so we're taking 6 times 5 times 4 times 3 times 2 times 1, and that's essentially what a factorial represents. And you have a factorial button on your graphing calculator. All right, so if you want to pull your graphing calculator up, if you select the math button and scroll over to probability, that's the PROB that you see on the top, you'll notice that the number 4 option in the list is that factorial value, okay? So I need to exit out of this menu. If I want to utilize my factorial, I need to input 6, and then I'll go to my math menu, scroll over to the probability menu, and I'll choose the 4th option from the list. And you can see that puts 6 factorial on my screen. So when we hit enter to calculate that, that comes out to be 720. So there are 720 different ways that we could write the letters A, B, C, D, E, and F. Okay? All right. So let's take on the second permutation rule then. The second permutation rule kind of expands off of the first. All right? It's the permutations of n elements taken r at a time. So in the first type of permutation, we were taking every item and arranging all of those items. In this second permutation rule, we're not taking every item. We're only taking a select few of them and arranging them. And that's what we see in our example problem, right? It says 8 horses are running in a race. In how many different ways can these horses come in first, second, or third? And assume there are no ties, all right? Now, the nice thing about our permutations is they're essentially fundamental counting rule problems. I don't really need to view this as a permutation. I could just view this as a fundamental counting rule, all right? Because I really just have 3 slots that I need to fill. I need a first place horse, a second place horse, and a third place horse, okay? So in this problem, we could just simply go, well, there's 8 horses possible that could win. Once one of them wins, then there's only 7 horses possible to get second. Once one of those gets second, now we're down to 6 horses in the third spot. All right, so we can just simply go 8 times 7 times 6 to come up with our permutation. All right, and so see how that's a fundamental counting rule. Now, the other option is to view this as a permutation, okay? And the formula for a permutation is we abbreviate it NPR. So in this problem, the N is representing how many items we have to select from. So it would be 6 permutation, and then the R represents how many items are you selecting from your given items. And in this case, it was 3. Okay. Now, if we work through just kind of the mathematical work of the formula, this is what that would look like. We'd end up with 8 factorial divided by 8 minus 3 factorial, which would be 5 factorial. And watch how we can simplify this down. So if I take my numerator number and I start to write it out as what the definition of a factorial is. So that's 8 times 7 times 6 times, and at this point I'm just going to write 5 factorial. I'm not going to keep expanding it because when I look at my denominator also has 5 factorial. All right? So the 5 factorials cancel out, and what we're left with is 8 times 7 times 6, which is the exact same thing that the fundamental counting rule gave us. All right? So we just want to make that connection between those 2 rules for you. Now, the nice thing about doing it as a permutation is we do have a permutation function built into our graphing calculator. So if we take a look at that here, again, pull those calculators out. Now we're going to calculate this 8p3, okay? So when you're calculating a permutation on your graphing calculator, you need to input your first number first, all right? How many items are you selecting from? In our problem, we had 8 horses. And now we're going to go into that math menu again. We're going to scroll over to PROB again. And you can see the second item in the list is this NPR. All right, so that's our permutation function built into our graphing calculator. So we're going to select that. And then I'm going to input how many items I want to select. So I want 8p3, and we end up with 336. All right. So that's our second permutation rule. Again, we can see how closely related it is to the first. So now let's talk about the third type of permutation. And this is what we call distinguishable permutations. All right. So if we have a certain set of objects, but some of those objects look alike, all right? If they look alike, it doesn't really matter if we put them in a different order. Take, for example, the word banana, all right? If I wanted to talk about how many different ways could I rearrange the letters in the word banana, well, if I switch the two ends, it still says banana, right? If I switch two of the A's, it still says banana, okay? So we want distinguishable permutations. We want something different, okay? Now, if I switch an A and a B or a B and an N, that's a different permutation. That's a different set of items now in terms of arrangement, okay? And so if we apply our formula, really what this is saying is, okay, N is representing all the objects that you have, okay? So how many letters are there in the word banana? Well, there's 6, right? So our numerator will be 6 factorial. The denominator is then the factorial of each individual item that we're working with, right? So we start with the letter B. How many B's are there? Well, there's just 1, right? So if we're being technical in the setup of the formula, we could go 1 factorial. Now the nice thing about 1 factorial, it's just 1, okay? Then we look at the A's, all right? Well, how many A's do we have? Well, we have 3 of them, right? And so if I rearrange those, it really doesn't matter. So there's 3 factorial. And then we have our 2 n's, 2 factorial. Okay? Now, one thing to be careful of is don't think, well, 3 times 2 is 6 factorial. The 6 factorials cancel out. We're good. No. Remember, 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. 3 factorial is 3 times 2 times 1. 2 factorial is 2 times 1. So we've got some different things going on here. All right? And so we could apply this problem on our graphing calculator, right? Open up my calculator here. All right, so again, just to practice our notation on our graphing calculator. So I'd go 6 factorial, so go into my math menu, PROB, oops, a little too far, get my factorial. All right, now in this problem, since we have multiple items in our denominator, it's going to be really wise for us to utilize some parentheses to make sure that we separate out everything that is in our denominator. Now I'm not going to take the time to type in the 1 factorial because 1 factorial is just 1. So we've got 3 factorial. And then we're going to multiply that by 2 factorial. Now you can save yourself a little bit of time with 2 factorial because 2 factorial is just 2, right? 2 times 1. So I'm not going to go in and hit the factorial there. We're just going to input it that way. So we can see there are 60 different ways that we can rearrange the letters banana. Now, notice how much different that was than our first example. If we go back to the 720 that we see on our calculator screen, remember that was how many different ways we could rearrange the letters A, B, C, D, E, and F. There were 6 letters there. Well, we also have 6 letters in the word banana. But the difference between our number 1 problem example and this example is the fact that, again, we have distinguishable permutations. All right, so let's go on to combinations then. Again, reviewing combinations. It says you are forming a 12-member swim team from 10 girls and 15 boys. The team must consist of 6 girls and 6 boys. So the question is, how many different teams are possible? All right. Now, what makes this a combination is compared to a permutation is the fact that it doesn't matter what order these people get selected. We're not placing them and ranking them. We're not signing them to a position. They just need to be selected, and if they selected, they're on the team. Whether it's first selection or sixth selection, a selection is good enough, okay? So the difference between a combination and a permutation is this whole idea of order, all right? Order doesn't matter here, all right? So let's just jump right into this example. Now, one thing that you'll notice in this example is that we do have kind of two different selections going on. We have a selection of the girls' team and a selection of the boys' team, and then we're going to combine these to make our total number of outcomes, all right? So we have two separate combinations going on here, all right? So let's start out with the girls, all right? Practice a little chivalry here, ladies first. So we have 10 girls possible, and we want to select 6 of them, right? So this problem will tell, or this combination setup will tell us how many different ways we can form the girls' team, and then we'd go 15 combination 6 to figure out how many different ways we can select the boys' team. Now, the way that we connect these two is using the fundamental counting rule, right? So we have two separate combinations, but if we want to combine these to see how many different ways we can select a team, it's going to be the fundamental counting rule that connects them. All right, so they'd be multiplied together. And again, you've got a combination function in your calculator, just like you do a permutation. All right, so I'm going to pull my calculator back up here. We'll walk through the setup of this. Now, again, I need to type in that first number before I go access my combination. So I'm going to go into my math menu, scroll over to PROB, choose the third option. All right, then I'm going to plug in a 6 here. Now I'm going to get out of my subscript, so I'm going to use my arrow key to arrow out. And now I'm going to set up another combination. So we've got 15. I'm going to go into my math menu, combination 6, and we can hit enter. And that's how many different combinations we can make. All right. So quite a few. Actually, there's an error there. You know what I needed to do on this problem? Hey, math teachers make mistakes too. I needed to separate these combinations with parentheses. All right, so let's try this again. Let's go 10, combination, 6. Close that parenthesis. Oops. Let's arrow out of the subscript first. Close that parenthesis. And then we'll go 15, combination 6. And I don't need to close that parenthesis since I'm at the end. Oh, we get the same answer. All right. I was a little worried that our calculator worked left to right there and saw 10 combination 615, which would be impossible anyway. All right. Never mind. You didn't have to use the parentheses, so we experimented a little bit together there. All right. So there's your combination. Now, as we talk about permutations and combinations, one of the big things we need to recognize is, again, does order matter or not? And as you read through problems in your homework assignment, you're going to have to determine whether or not order matters. And so the key is going to be looking for key words. So just some words that we can think about when we think about permutation. Order, arrangement, if we're giving awards, if there's a seating chart, if there's a ranking, all of those words specify order. All right? In terms of a combination, if they just say something like select or choose, or they might even come out and say order doesn't matter, right? All of those things pop or point towards a combination. Now, there may be times where you'll see select a certain number of items and arrange them. All right, if we see a combination word and a permutation word together, the permutation word takes precedent. Okay, so those are some important words just to keep in mind as well. All right, we've got one last example that we wanted to walk through with you today, and then we'll call it a wrap here for our Chapter 9, Section 6 video. All right, so a problem using permutation in kind of an equation setting. And we just want you to be able to think through the algebra of things here. And this is just in preparation for just a type of problem that we're going to see down the road here. Okay? Now, this problem is actually pretty easy if you know your permutation formula. So a reminder here about what our permutation formula is. Our permutation formula said NPR is equal to n factorial divided by n minus r factorial. So I'm going to use that in the setup of this problem, okay? So if I set up my two permutations, so that means on my left side I would end up with n factorial divided by n minus 5 factorial. And this will be equal to 18 times, and we'll set up our factorial notation over here, will be n minus 2 factorial divided by n minus 2 minus 4 factorial. Okay? Now, these problems become really easy if you understand how to simplify factorial notation. Okay? So again, remember what a factorial represents. Okay? A factorial, when we had 6 factorial earlier, that meant 6 times 5 times 4 times 3 times 2 times 1. We're decreasing by 1 unit on each sequential term. Okay? So if I have n factorial, I need to subtract 1 from that to make the next sequential term in a factorial notation. All right? So that would be n minus 1. Right? And then I need to subtract another 1 from that. Right? So what we create is this sequence. Right? We keep taking n and decreasing it by one number smaller. Okay? And then I'm going to get to the point where I have n minus 5 factorial, and I'm going to stop there. Because again, remember, when we're simplifying factorial notation, right, when I'm at n minus 5 factorial, that now matches to the denominator of n minus 5 factorial, and I'm able to simplify. So these n minus 5 factorials cancel each other out. And we can do that same thing on the other side. All right? So the other side would be equal to 18 times, start at n minus 2, and then create each sequential term. Well, after n minus 2, we go n minus 3, n minus 4, running out of room, n minus 5, and n minus 6, and then I'm going to put a factorial there and quit. And this is all over, n minus 6 factorial. So those n minus 6 factorials cancel out. Okay? And now, the nice thing is, if I look at terms that I have on each side, well, I have an n minus 2 on each side. All right, we have an n minus 2 term. So n minus 2, if we divide both sides by n minus 2, those cancel out. The n minus 3's cancel out on each side if we divide by n minus 3. The n minus 4's cancel out on each side. Right? And now if we look at all we have left, on the left side, all we have left is n times n minus 1. On the right side, all we have left is 18 times n minus 5. Well, this just turned into a pretty simple algebra problem, right? So we distribute here, we got n squared minus n equal to 18n minus 90. Right? We rearrange all our terms. Let's get them all on the same side. So we end up with n squared minus 19n plus 90 is equal to 0. This is factorable. So into n minus 10 and n minus 9. Excuse me, that's my wife. All right, folks, I'm sorry about that. So just to finish out our problem here, so we've got n minus 10 and n minus 9 equal to 0, so n would be equal to 10 or 9. All right, that brings us to the end of our chapter 9.6 video. I want to remind you there's also 9.7 video, and I just want to encourage you to make it a great day. All right, we'll see you guys soon.